Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working on problem number 3.42. The problem statement says, the level of toluene, a flammable hydrocarbon, in a storage tank may fluctuate between 10 and 400 centimeters from the top of the tank. Since it is impossible to see inside the tank, an open-end manometer with water or mercury as the manometer fluid is to be used to determine the toluene level. One leg of the manometer is attached to the tank 500 centimeters from the top. A nitrogen blanket at atmospheric pressure is maintained over the tank contents. All right, here I've got a picture of the diagram that they gave to us. And let's read part A. When the toluene level in the tank is 150 centimeters below the top, the manometer fluid level in the open arm is at the height of the point where the manometer connects to the tank. What manometer reading, R in centimeters, would be observed if the manometer fluid is 1. Mercury, 2. Water? Which manometer fluid would you use and why? Okay. So we've got our tank here. We have the tank toluene level kind of fluctuates between 10 centimeters and 400 centimeters, but we're 500 centimeters down, attached right here. And this level is equal to this level when the tank level's at 150 centimeters. Okay? We need to figure out what R is. So they gave this information to us. We need to figure out what R is. We're going to solve it generically first, and then we'll just substitute in the water and mercury values as needed. Okay? So what we need to do first, let's take a look here. We need to figure out what the pressure is at PA. And then once we figure that out, whatever the pressure is at PA in both legs should be equal to each other. And so if we figure out what the pressure is at PA, then we can solve for what R is. Okay, so in the left leg, PA is equal to the atmospheric pressure above the tank plus the density of toluene times gravity. So we need Z, right, times Z. So Z in this case is equal to R, all of this height, R, plus 500 minus 150, which would be this distance, 500 minus 150. So we've got this whole distance right here, which is 500 minus 150 plus R, and times the density of toluene. All right, so that's what we've got right here. Remember, if we're working in pascals, we need to convert our height and units and things so that they're all consistent. That's why these are in meters, 5 meters minus 1.5, because they gave it to us in centimeters, so we're just converting into meters here. So we've got our atmospheric pressure plus the 5 meters of toluene plus minus the 1.5 meters that we're not doing anything with. It's just open space or air, which we've already counted for in the atmosphere here. And then we have this R term that we don't know what to do with. I'm going to go ahead and call this number C, so I don't have to keep writing the number over and over again. Okay, so C plus this density times R. That's the left-hand side. Now let's solve for the right-hand side. So the right-hand side is equal to P naught times the right-hand side leg. And the right-hand side leg we know is, okay, we've got all this pressure that's just the atmospheric pressure, plus the density of whatever our manometer fluid is, times this height, which is just R. Okay, so atmosphere times the manometer fluid head, and we can set these two pressures, PA, equal to each other and solve for R. So that's precisely what we do over here. We set them equal to each other and we solve for R, which equals this. And we have everything in generic terms, so now we can just substitute in what our density is for mercury versus our density for water. Okay, and this is what we solve for what R is for water and mercury. You can see that mercury is about 100 times less head than the water. Okay, so in order to save on materials, so you don't have to have a 22 meter long manometer, how about we use a manometer that is instead about 24 centimeters long, and we use mercury instead. That is why I would choose mercury as the manometer fluid, because the manometer would be much smaller and easier to manage and measure. Okay, now part B. Briefly describe how the system would work if the manometer were simply filled with toluene. Give several advantages of using the fluid you chose in part A over using toluene. Okay, so the level in the manometer would be the same as that in the tank. So if the whole thing was just full of toluene, then the level would always be the same as that in the tank. So that's how it would operate if it was just toluene. Now let's talk about some of the advantages. Mercury in water may have a lower vapor pressure than toluene, and toluene is also flammable, so having it open to the atmosphere could be a little dangerous. And you might contaminate stuff in your toluene if you don't have that manometer fluid protection barrier, so maybe there's a risk of contamination getting into your tank. Okay. Now let's go to part C. What is the purpose of the nitrogen blanket? Now this one actually took me a little bit of thinking. I was like, why did they pressurize it with just the atmosphere pressure of nitrogen? That is a little odd. But then I realized that toluene, in the very beginning of the sentence, they said is a flammable gas. And I said, well, what is the difference between nitrogen and air? Well, it's the oxygen. And then I went, oh, duh. If you have oxygen over a flammable gas, that's a hazard. Okay, so they just fill the whole tank with nitrogen, get rid of all that oxygen, then there's a lot less risk of fire starting. So that's the main reason for the nitrogen blanket, I assume. All right, well, that is it for problem number 3.42. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.